In this video, I'm going to show you how to find the vertical and horizontal asymptotes of a rational function by using limits. So here we're given a function. It's f of x is equal to x squared plus 2x plus 1 over 3x squared plus 4x plus 1. So it doesn't really tell us what to do in terms of limits. So we have to sort of walk into the problem knowing how asymptotes are defined using limits. So the next slide is a bit of review or background knowledge you have to do problems like these. A function has a vertical asymptote at a number like c, like x equals c, when approaching c from either direction, either from the right or from the left, you get either a positive or negative infinity. So if you approach c from either direction, the function will explode either real big or real small if it's positive or negative infinity. And horizontal asymptotes are pretty much the inverse. Here we approach a finite value and get infinite results. For a horizontal asymptote, you approach infinity and get a finite result. And that's true for positive or negative infinity. So horizontal asymptotes tend to be a little bit easier to find in general. You just have to walk in knowing that you need to take the limit at infinity. Vertical asymptotes are harder because it's not going to tell you what c to use, and there's some ways to find a good candidate for value of c, or maybe even multiple values of c. So let's do the easy part first, which is the horizontal asymptote, which means take the limit at infinity. So here's our function, and let's see if we can find the horizontal asymptote. So if I take the limit as x approaches infinity of the function, let's see if I still have it pasted here. Nope. I'll just try it again. X squared plus 2x plus 1 over 3x squared plus 4x plus 1. There's a variety of ways you could do this, including dividing everything by x, but the fairly straightforward way I've found is just to plug infinity in using direct substitution. It's not quite mathematically sound, but it's going to give you the idea in terms of function dominance. So we have infinity squared plus 2 infinity plus 1, and on the bottom we have 3 infinity squared plus 4 infinity plus 1. And here's where you really have to think about the unimaginably large size of infinity. On top, I have infinity squared plus 2 infinity plus 1. And I think we can agree that as infinity grows, and as the value of x grows, which is really what this is saying, the plus 1 here is not really going to matter. It's a rounding error compared to how large infinity is. And moreover, even though we have 2 infinities here, infinity squared is immeasurably larger than that. So in the same way that adding 1 is sort of, child's play, adding 2 infinity is also child's play compared to the vastness of infinity squared. And the same rationale holds true on bottom. Adding a constant is going to be dominated by adding 4 infinities, which is further dominated by this term right here. So the dominant term in both the numerator and the denominator is the highest power, in this case infinity squared on top and 3 infinity squared on bottom. And these two guys grow at the same rate. So if I plugged in a trillion on top and a trillion on bottom, the ratio is going to sort of get closer and closer and closer to what you can probably see here as 1/3. So on top I have basically 1 infinity squared, on the bottom I basically have 3 infinity squared. And again, the reason I can ignore all the business that I've marked out is it's being dominated by the larger degree. I think I said coefficient earlier, I meant exponent, apologize for that. So these would effectively cancel because they grow at the same rate, giving us 1/3. So based on the definition of a horizontal asymptote, if we approach infinity and get 1/3 as a result, or a constant as a result, our horizontal asymptote would be the function y equals 1/3. So let's take a look at vertical asymptotes. So it's a little bit more challenging because, again, it does not tell you which number to approach, whereas we knew that from the get-go here. So let's see if we can find some candidates for vertical asymptotes. We do that by factoring the function and seeing if we can find any values hidden within its description. So on top I would have x plus 1 times x plus 1. And on bottom I would have, let's see, 3x and x. Factors of 1 make it easy. It would have to be these right here. Make sure this works out properly. 3x squared. 3x and x makes 4x, and then 1 times 1 is 1, yes. Now, one thing you'll notice here is that the x plus 1 term will cancel. which means even though the value -1 would make the bottom equal to 0, it is not going to be a vertical asymptote because it can be removed from the function. As we've later learned, that's a clue that it's a removable discontinuity. So our function is really, in its sort of final form here, x plus 1 over 3x plus 1. And now we ask ourselves the question, well, what can I not divide by? Or what can I not plug in here? Or what causes me to divide by 0? Which means set the bottom equal to 0 and solve. So it would be 3x equals -1, which would be x equals -1/3. That's our candidate for a vertical asymptote. That's our c value that we're going to take the limit at. So now that we have our candidate, let's take the limit as x approaches -1/3 of our new and improved function, our simplified form, which is x plus 1 over 3x plus 1. Now you'll notice if I plug -1/3 in here, I'm going to get 0 on bottom, and recall you cannot divide by 0. And we can't factor it anymore either, so we have to take a one-sided limit. So I'm going to choose to come at this from the left, but really any direction is fine. So on top, I have, let me just rewrite this here, so we see in green what we really need to do. So if I plug in 1/3 here, 1/3 from the left here and here, I would get -1/3 from the left plus 1. And the bottom I would get -1/3 from the left plus 1. I'm going to be a little imprecise on top. -1/3 from either direction plus 1 is going to take me back into the positive region. So that's going to be some sort of positive number. Looks like it'll be 2/3. But it's a positive 2/3 in any case. More important is the bottom, because I need to figure out what type of 0 I'm going to get, from the right or from the left. So just as a rule of thumb, this would be let's see, this is -0.3 repeating, so this is probably something like 0.344, something like that. It's from the left. So multiplying that by 3 will give me a number slightly bigger than 1, but it's going to be negative, so -1 from the left. So make sure you can walk through those steps of how to determine what type of -1 this is. And then I'm adding 1 to that. So this is a placeholder for -1.001, basically. Plus 1 would give me a negative result, but a very, very small negative result, which we signify thusly, which will give me a positive over a negative, which is a negative, and a finite value over an infinitely small value will give me a -infinity. So because I approached a finite value and gotten an infinite result, this tells me that this function has a vertical asymptote at x equals -1/3. That's the location of the vertical asymptote. That's where the dotted line would occur, so to speak. All right, hope this helps.